Hello and welcome to the lecture of strength of material. In this lecture, we are going to talk about the deformation in the composite bar, particularly the bar in series connection. So, as we know that when we deal with the structures, particularly with the bar kind of structure, there may be a series connection of bar or parallel connection of bar. For example, if our structure is like that, there are two bars connected axially. Both the bars are having different cross section and I am applying a force P at the end of this bar. Other end is a fixed end. So in this case, what will happen if I will apply a force P here? The same force is going to transfer in the second bar. That means the load experienced by both the bar will be P, but if I will see the deformation, the total deformation will be the summation of deformation of first bar and the second bar. On the other hand, if I will see the other kind of structure where the two bars are connected in parallel and I am applying a force P which is going to be distributed in the two bars. So my force equation will look like that. Total force will be the summation of the forces in individual bar. But here if I will see the deformation will be equal in both the bars. So my second equation about the deformation will be del 1 is equal to del 2. So now in this lecture we are particularly going to focus deformation in the bars in series connection. So here I am showing you one picture. It is a very typical problem. You can find it problem in all the books of strength of material. So here I am showing that there are two bar 1 and 2. Both the ends are fixed end and I am applying a point force P at the junction of the two section. And now I will be interested to find reaction at these two ends as well as the stresses in the two bars. So suppose I am assuming, I am just showing you how you can solve this problem. So what the first step, what you can do, you can assume reaction at the two end. Normally I consider reaction in the same direction. Irrespective of that whether the force direction is left or right, I generally assume the direction of the reaction same, maybe rightward or leftward. So now I have to start making the free body diagram of each section, each bar. For example, if I am starting with the bar 1, I will put a force R1 here. So I know that this would be my force R1 on this bar. As this is R1, I should not think what would be the force at the other side. Simply I am going to put that this, as the bar will be in the equilibrium, so other force will also be R1. Now when I am going to make the free body diagram of the second bar, here I will take care of this force P. So one force which is equal and opposite to the R1 will be here and another force will be the P force. So now there are two forces, one is R1 force, another force is the P force. Now I have to decide that the net force will be a compressive force or a tensile force. It depends on my assumption. Suppose I am assuming that the P is greater than R1. So this is P force and this is R1 force. So I can assume that now my net force will be inside and the magnitude of force will be P minus R1. As this is P minus R1, similarly this will be equal and opposite to the P minus R1. But if I will go and I will see that I have already assumed a reaction of magnitude R2 here. So that means the R2 is equal to P minus R1. So I will get one equation for this system that will say that my P minus R1 will be equal to R2 or R1 plus R2 will be equal to P. If I will carefully see my system, definitely when I will apply certain force here, some of the portion of this force will go to this bar and some of the portion of this force will go to the second bar. So my total force will be distributed among the two bars, so P should be equal to R1 and R2. Now as I know that the total length between the two support will remain L only. That means whatever will be the change in length of this bar, the exactly same and of the opposite nature will be there in the second bar. For example, if I am assuming that there are force R1, R2, then that means the whatever change in the length will be, the length is going to be increased in this bar. So for the second bar, the change in length will be same, but it is going to be decreased, means there is a compression in the second bar and there is an extension in the first bar. So my second equation, which is coming out because of the deformation, or I should say the compatibility equation, that would be del 1 will be equal to del 2. If I will further elaborate it, if I know the cross section area of both the bars, let A1 and A2, material may be different or may be same. Suppose material is same at this case, so the Young's modulus or elastic constant will be E, and I know the individual length, that is L1 and L2. So my deformation equation will say that the forces in the first bar will be R1, length is L1, divided by the cross section area A1 and Young's modulus E1, that is going to be balanced by the forces in the second bar, which I have assumed either R2 or P minus R1. So I will put R2 and then I can use this equation to put the value, or directly I can use that. So I will get that P minus R1 into the length of the second bar L2, then the cross section area and the Young's modulus. So now this is my final equation. From that I can get the value of R1 if I know the P value, and once I will get the R1, I will get the second reaction force. There may be different types of problem. Instead of having the 2 sections, I may be having the 3 sections, and here also I have to apply the same philosophy. So here you can first make the free body diagram of all the components. Here you can see that in the first question my force was acting at the junction. So here I have a freedom to consider only 2 sections, but if I will see my second problem, here my force is acting at this point. So there are different methods available in the book. People also use the superposition method, where they consider only one force and find the change in the length in all the section. Then they ignore the first force and the third force and use second force, and again they find the change in length. Similarly, they consider only one force at a time, find the deformation in each section, and they finally add up all the deformation with respect to their signs, and this method particularly known as the superposition method. I believe that this is a little longer method, so instead of that, what we can do, if we are having forces in this way where the forces are not acting actually at the junction, instead of that forces are acting in between somewhere in your body, so what I will do, I will consider this part as section 1. Then this is section 2. This from here to here, as the cross section is changing, again I can make a next section from here to up to here only. Then from here to here I can use another section, and from here to here I can use another section. So in that way I'm going to consider 5 sections. So here is the free body diagram of 5 sections, and as I can see here, that I already explained in my previous case, I am going to consider my reaction in the same direction here also. So my reaction R1 and reaction R2. Here also we are interested to find the reactions as well as the forces in each section. After getting the forces, we can get the stresses in each section. So for the first section, this is one end, I can start either from this side or this side. Let's start from this side. So first this force is going to be here, that it would be R1. As this is R1, no need to think what is on the other side, simply put R1. Once I will get the R1, this R1 I am assuming that it is there because of the next section. So equal and opposite R1 will be here. So this would be the reaction of this R1. Now I will consider this force P1, which is acting in this direction. So this is my P1. Again I have to think whether the P1 is greater or R1 is more. If I am assuming that P1 is more, that my net force will be a force of compressive nature, and total will be P1 minus R1. As this is P1 minus R1, no need to think what would be on the other side. Simply put a force P1 minus R1 on the other side. As this is P1 minus R1, and as per my convention, it is going inside this body, and equal and opposite P1 minus R1 will act here. So this will be again P1 minus R1. This is P1 minus R1, so I am going to use the same P1 minus R1 on the other side. Now when I will talk about this fourth section, here I have to consider the force P2. So this P1 minus R1 having an equal and opposite value here, so this is my P1 minus R1, and also I am having the force P2. So here also I have to think whether P2 is greater than P1 minus R1 or P1 minus R1 is more. So if I am assuming that P1 minus R1 is more, I will consider an equivalent force that will be P1 minus R1 minus P2. So equal and opposite P1 minus R1 minus P2 I am going to put here, and again when I am going to shift or consider this force as equal and opposite here, this would be my P1 minus R1 minus P1 minus R1 minus P2, and the P3 is also acting in the same direction. So the P3 is also here, so I will put this P3. So finally this force which is acting at this side will be going to balance on the other side. However, I have already assumed that the other side reaction will be R2, so R2 will be nothing but the P1 minus R1 minus P2 plus P3. If I will rearrange this term, I will be able to get that the P1 minus P2 plus P3 is going to be balanced by R1 plus R2. So this is my equation which I am getting by using the free body diagram. The second equation which will be there because of the deformation. So now there are different ways to write this equation. What I do here, once I have decided the direction of the forces, as I have decided the direction of the forces, I know which force is of the compressive nature and which force is of tensile nature. As in my case, this is a tensile nature force, so let's assume that this is del 1 of plus. It is going to be, the length is going to be increased. When I will see the second case, I have assumed that the P1 is greater than R1, so the nature of force here will be of compressive, so I am going to use this is minus del 2. Similarly here also I have assumed the compressive, that this will be minus del 3. This is also compressive, to minus del 4, and here also it is compressive, to minus del 5. So ultimately if I am going to write the equation for the deformation, I will say that plus del 1 minus del 2 minus del 3 minus del 4 and minus del 5 is going to be 0 because the total length is not going to be changed. Now when I will put these values del 1, del 2, del 3, I am going to use R1 term for del 1, P1 minus R1 for del 2. So my final equation, if I will write here, that will become that R1 length of the section L1 divided by cross section of A1 and E1, then minus sign, and my force value will be what? P1 minus R1 length of the section L2, then A2 and E, then minus this again P1 minus R1 L3 divided by A3 and E. Similarly minus this fourth one is having a value of P1 minus R1 minus P2 into the L3 divided by A4E, and then I am having a next last one that would be equal to minus P1 minus R1 minus P2 plus P3, or I can write it as the R2 and then I can replace the value. So this would be L4, L5, this is L4 and A5E. Finally it will be 0. So this would be my final equation for the deformation, where I have already considered my force balance equation. So when I will solve this equation, I am going to get the value of R1. Once I will get the value of R1, I can use this equation to get the value of R2. As I will get the forces in each section, if I am interested to find the stresses in each section, my stresses in the first section will be what? R1 by A1. Stress in section 2 will be the forces actually P1 minus R1 by A2, and if I will find finally that this exact term is coming out positive, that means the nature of force here would be compressive, because my force is going to act inside the body. That means the change in length will be compression, will be compressive type. So the nature of the stress will be compressive. So it depends. When you will finally get the force value, then only you will be understand that the nature of the stress will be compressive or tensile. This part we are going to understand when we will solve a numerical. That I will going to show it in my next lecture. So ultimately I am going to close this session with this third example. If you will see books, you will find number of examples. So these three are the basic problems. If you will understand writing equation for these problems, you will be able to handle any kind of problem. So this is my case where I am again having the two forces P1 and P2 acting here. I have assumed the reaction R1 and R2, and as I said, there will be free body diagram. So first I will start from the R1. Here R1, so it will be R1. This is R1, so the R1 will be here, equal and opposite. As I am having P1 force, so P1 will come here. Now if I am assuming P1 is more than R1, so I will put P1 minus R1, and the direction of force will be the direction of P1 because I am assuming it is more than R1. So equal and opposite will come on the opposite sides, as this is P1 minus R1. Equal and opposite will come here, P1 minus R1, and there another force P2. So now finally I am having P1 minus R1 minus P2, and direction will be again inside because I am assuming this whole term is greater than this term. So the net force going to act on this body will be of compressive nature. This is R2, and this force will be P1 minus R1 minus P2. So finally, when I am going to see that R2 will be equal to the P1 minus R1 minus P2. So this is my one equation. When I will see the deformation equation, as per my convention, there will be a positive change in length. So del 1, there will be negative to del 2, and there will be negative to del 3. So my final deformation equation will be del 1 minus del 2 minus del 3. When I will put the deformation value, as I have already explained you for the previous cases, that del 1 will nothing but the, if I will write for the del 1, it will be R1, length of the first body, A1 E. If the material is same, then minus the forces for the second one is the P1 minus R1, length of the second body, A2 E. And third one will be again the minus P1 minus R1 minus P2, then length of the third part, A3 E, is equal to 0. So for using this equation, I will get the R1 value. As I will get the R1, I will use this equation to get R2, and then I will know the forces in each section. After getting the forces, I will be able to get the stresses in detail. If you want to see, you can see my next lecture where I am going to solve a numerical. So here again I am just giving a brief that this is the case where we are having the bars in series connection, and in this fashion you can get the reactions at the support. All these problems I have shown here are statically indeterminate problem, because we need the deformation equation and the force balance equation, then only we will be able to get the reactions. Thank you.